All right, welcome back to part three here of homework one, my homework one. Um, let's hop right into it with our usual phone, desk, and face scan. And so, cylindrical barrel, a cylindrical barrel of radius r and length l is lying on its side, i.e., oriented such that the barrel can roll. As I have already drawn here, when the fluid level in the barrel is h, calculate the horizontal pressure force on one circular end cap and one cylindrical half. And so let's start off with this one cylindrical half here. So we know that the pressure force here is equal to the pressure times the area that it's acting upon. And so the pressure force will always be normal to whatever surface that is. So if we think about it, um, the liquid right at the surface of the cylinder is going to be the one enacting that pressure force. But we can also say that the liquid behind the fluid behind that surface fluid is also applying a pressure force on that surface fluid. And so if we keep on saying that, it's going to get to the point where the maximum, the sort of, I guess, origin of all the pressure force can be said to be at the center of that barrel of fluid, right? And so if we imagine sort of a rectangular plane stretching from one end to the other end at the center of that barrel, so sort of like this, right? I'll draw it here too. Sort of like this. And that will say that the pressure force originates from there. We can sort of calculate the pressure force there instead of at that surface of the cylinder, the barrel, the surface of the barrel. That will make the calculation a lot easier. And this works, right? Because if you sort of imagine that this rectangle is sort of pushing out, right? It fills up that entire cylindrical surface eventually, right? And so that's what we'll be doing. And it works too. And so with that in mind, we know that since this is a fluid, pressure is going to be calculated from rho gh, something that we found through our basic equation of fluid statics. And so, like I said, the pressure force is the pressure enacting on a certain area. Well, since pressure is changing as we decrease in height, having the bottom of the barrel being 0, so decreasing in height, that area, so I'm going to have area strips here, so area strips here, and we're doing strips because in the horizontal, because pressure is constant horizontally, these area strips, in order to get to the total pressure force on the entire cylinder, we'll have to sort of add up all the different pressures as you go down, or up, I guess I should say. And because of that, our summation of these different pressures at different heights are going to turn into summations of different pressures at different with different areas. So our differential area is going to turn into differential height. So how do those two relate? Well, if we use our strip that I have already drawn here, the differential area is going to be equal to that differential height, right, times the length of the barrel, L. So that's super simple. And so summing up all the different pressure forces, so that will be an integral. It'll be from the bottom of the barrel to the fluid height of the fluid. And so we can then plug in our things that we just derived, and we'll get force is equal to the integral of 0 to h of rho gh times the length of the barrel dh. These are dummy variables of integration, and so when we integrate, rho g l all come out because they're constants. The dummy variable becomes h squared over 2, and This is evaluated from 0 to h. If we were to plug in 0, all cancels out, disappears. And so we're just left with plugging in h. And so ultimately, this is what we get as the equation for our pressure force on one cylindrical half. And so that was super simple, right? So having to sort of represent our differential areas for our different pressure forces in terms of dH, that sort of process. It's super simple, at least for this case. And so moving on to the more difficult side of things, we have our circular end cap. And so since we're just dealing with the circular end cap, we can sort of change our point of view on this barrel to being just that circular end cap. So we're looking at it head on. So our fluid height is right there. H, we have the center of our circle. And we won't need L at all since we're looking at it head on. So how do we start with things here? Well, we know the radius, right? The radius is R. And I'm going to sort of denote everything in polar coordinates. So we'll have this right here be our 0. And so we're going to sort of approach this with the same approach for the cylindrical half, where force is equal to the summation of all the different pressures with the pressure with the differential areas times the differential areas, right? That summation. And so how do we get at, first off, these differential areas, right? And so on. So just writing out the equation first, right? Same notation and everything. What is so we know that pressure is already equal to rho GH. Just looking at that equation first here, we don't know, we can't use exactly H since we're in polar coordinates, so we'll have to sort of define H in polar coordinates, which is typically in theta, terms of theta, right? So we'll have to do that. Our differential area needs to be defined, right? Like we did earlier for the cylindrical half, that ended up being DHL. So since it's in polar coordinates, it's going to deal with d theta as well. And we also need our bounds of integration, our limits of integration here. And so let's start off with our limits of integration. So we know that it'll be going from up here, which I'll just denote as theta 1, all the way to down here, which will be negative pi over 2, since this is theta. So going 90 degrees down, it's negative pi over 2. And so we can solve for 1/2 and then just multiply by 2 to get the other half, to get the full pressure on the circular end cap. And so we have our bounds of integration now. It will be from up here all the way down here. So basically this entire height, which so it works out. So, and now we have an issue. Well, starting from the top, going to the bottom. And so, what other things can we solve here? Well, theta 1, right? So we know that this right here is h minus r, since this is also the radius. So h minus r gives us this height. And so we also know then that sine theta 1, or just for now, sine theta, is going to be equal to the hypotenuse, opposite, which is h minus r over the hypotenuse, so r. So we now have that established relationship, right? And so ultimately we can now solve for theta 1, which I'll write out later. And then we're also given well, we can do some manipulation here, and we can see that r sine theta is equal to h minus r as well. And so, like I said earlier, we're going to need h here in terms of d theta, or I guess theta, I guess. So we find, just from this equation, we can see that h is equal to r plus r sine theta. So we can sub that in. And we also know that so moving on to the differential area here. So since we just solved for h, we know that it's going to be horizontal strips again, right? And if we were to draw the radius here, we can find the length as we did earlier. And so it's going to be dA is equal to r cosine theta. So that's our length. And it's going to be some differential height, right? So dh. And well, since we solved for h here, we can just derive this to get dh. So we'll have dh is equal to r cosine theta d theta. And so that's where our d theta comes in for dA. And so dh times the length, ultimately dA is going to be simply r squared cosine theta d theta, cosine squared theta d theta. And so I'll just write r plus r sine theta here, just to show that we solve for it. And so now we can sort of plug everything in now into our force equation. So we get the integral from theta 1 to negative pi over 2. We get rho g times r plus r sine theta times r squared cosine squared theta d theta. And so we can now finally simplify everything to get towards our expression for the force of the pressure force on this circular end cap. And so, gosh, distribution, let's start off with that. So we'll get rho g r cubed cosine squared theta plus r cubed sine theta cosine squared theta d theta. Parentheses there, still an integral force. Pull out the r cubes. Rho g r cubed cosine squared theta d theta. We can split the integral now. Actually, let's split the integral the next step so this doesn't look so messy. Plus sine theta cosine squared theta d theta. Alright. I'll split the integral now. So we'll have force is equal to, I'll pull out the rho g r cubed since those are constants. Rho g r cubed integral theta 1 negative pi over 2 cosine squared d theta, cosine squared theta d theta, plus the integral on this side, sine theta cosine squared theta d theta. And let me make sure that's the same. Yeah. All right. Now, all we have to do is integrate this and then simplify the resulting expression. So I won't be doing these integrations by hand, which is why, if you might have already noticed, I have the let's solve it via computer. That's why we have it, right? I just put in x, I'll just sub in theta afterwards. So we have, so f is equal to rho g r cubed, and then we have, put a bracket here, So we have theta over 2 plus sine theta cosine theta times 1/2. All right, integrated from theta 1 to negative pi over 2, and that is added with the integral of this expression. So sine x, and we get so negative third, so I'll get rid of this plus sign here, negative third cosine cube theta integrated from theta 1 to negative pi over 2. All right, and so end bracket. Now continuing to simplify here, we have for this side, so I'll rho g r cubed out again. This side, whenever negative pi over 2 comes into a cosine, that just becomes 0. So firstly, we have negative pi 2 into here, turns it into negative pi over 4. This becomes 0. So we have minus the theta 1 term. So I'll just leave that blank for now. And that this might get messy. So I might mess up here if I don't deal with the theta 1 term now. So theta 1 is equal to, well, we said that sine theta is equal to h minus r over r. So to get theta, we'll just have to do the arc sine of that. So we have sine of negative 1 over h minus r over r. And then using sine theta as our reference, so we gotta remember that theta 1, this was for theta 1, right? I just kept it that way so that we could find the expression for h, but now for theta 1 is equal to h minus r over r, right? And so if we square, I'll keep that. If we square everything, so we get sine theta 1 sine squared is equal to h minus r squared. We can say that this is equal to 1 minus cosine squared theta 1. Do a bit of rearranging, and we get cosine squared theta 1 is equal to 1 minus h minus r squared. Do some fraction stuff, and we get I'll square root it too at a time. Square root, common denominator, r squared minus h squared minus 2hr plus r squared, right? So h squared, negative r squared is plus r squared. H times negative r is minus hr, 2 of those minus 2hr. And that's all over, since I square rooted it already, r. And then this gets simplified to 2hr minus h squared r. All right. And so using this, we can simplify this a lot further. And so putting theta 1 into this, we get 1/2 times sine negative 1 h minus r over r plus, or I guess I didn't have to put this out here if I just apply the negatives now, minus plugging theta 1 into this part, so 1/2
you get h minus r over r times cosine of theta 1, which is rad 2hr minus h squared all over r. And then, all right, then we have 0. So then we just have to evaluate it for theta 1. Since it's this is the second value, it's technically minus, right? So it's 0 minus that. So this turns into plus. So plus 1/3. So it'll be this cubed. So we get 2hr minus h squared to the 3/2, because that square root was still there, and then r cubed. And then n bracket can't fit it, but it's there. And so there's our force equation for the circular end cap. A lot of work, a lot of concepts that you have to apply to make it simpler, right? So, thank you.